Buongiorno.
Anche buonasera, probabilmente.
Buonasera,
Visto
sì.
che tu sei pure in Italia, credo.
Esatto, a casa. Tu sei ancora in ufficio?
Eh sì, perché ho finito un meeting alle 7:10, per cui non ho voluto rischiare di tornare a casa, perché magari beccavo un incidente. Poi
Ok,
venerdì
sì,
sera c'è traffico il venerdì. Io abito in centro, per cui...
ottimo.
Vabbè, mi senti bene, quindi.
Sì, benissimo.
Ok.
L'ansia?
No,
No.
not really.
Not
Only
really.
afraid I'm talking too much. That's the usual, what this makes
Ah,
me
ok,
especially afraid most of the times.
ok.
So how
You
long?
have
How long?
45
45
minutes
minutes.
plus
Okay.
15 minutes for questions. Or if you want, we can. So do you want people to stop you and for making questions, or you want to go straight?
I don't know what is the usual habit. For me, it's right the same.
Usually
I
at the
don't care.
end.
At the
Usually at
end,
the end.
as you
Yeah,
prefer. For
probably
me,
on Zoom it's better at the end because if
hmm
not, a lot of confusion can be created.
hmm hmm So you're telling me when I don't know, like I have, I don't know, like 10 minutes to go or something like that.
Okay.
Hello,
Yes.
because I don't know, I can talk for hours maybe. So depends. Unless I'm a bit hungry because I have no dinner yet. So maybe I'm going quickly because I'm hungry.
Because you want to eat something, yeah.
My
Makes
dinner.
sense.
Hi, Marco. I'm Anna Vasari.
Hello.
You're at Mission.
Hi, Anna.
Hi, Jakub is Jakub or Jakub? What's the
Jakub.
correct name? Yeah.
Jakub. Yeah.
Yes. Good. Thank you. Well, thank you for making time in your schedules on Friday evening. We really appreciate it.
No problem.
We
My pleasure.
watched this. Thank you. We watched the seminar as a group here at MSU, so I'm going to rename myself. And in a few minutes, I have more people around and they might ask questions also. I
Okay,
can
great.
see your screen.
Can you see my screen?
Yeah.
Yeah.
Mhm. Okay. How can you hear me? Is it clear?
I hear you
Okay.
super clear.
Sounds clear,
Okay.
yep.
Mhm.
So you've put Etna on the first page.
Yeah.
Nice.
Then the talk is about does nothing, It's not geology or whatever.
Yeah.
The only nice picture in the talk, indeed. So at least one nice picture. It's
I hope you
necessary,
have
no?
some experimental setups as well, right?
I don't think I have any. Yeah, but maybe I don't remember. Maybe
Only theory and
only
equations.
equations. Yeah, a lot of equations, indeed. Yeah, no picture. Yeah. Oh well, not really.
Ah, but there are some nice plots.
Uh, I got some cold, so maybe from time to time I'm gonna stop.
No. Yeah. the weather was not so great last week.
Yeah, at some point it got nice, and then temperature just dropped. But in reality,
Yeah.
you don't know how to, because like overnight it's cold, in the day it's hot, so you don't know what to put on.
Yeah,
essentially.
exactly.
And there is pollen all around.
Yeah. How
Can
is
you
it
also see
going
my
at the?
pointer?
Yes,
The
yes, I
pointer,
can
okay.
see.
So the
How is
experience
it
we made. Sorry?
How is it going at the Laboratory del Sud? Are you measuring
No,
something?
no. Probably this I'd say in next fall, like I don't
Okay.
know, November maybe.
Okay.
We are waiting for authorization from several authorities after the upgrade and at least of the
Okay.
tandem. So it's we are like lost in bureaucracy, not lost in translation.
Okay. I can understand it. I know how it works in Italy.
Yeah.
So authorization from radio protection, from fire brigade, probably as well.
Yeah. All things like this.
And what was the upgrade? You upgraded the accelerator?
Well, we have here cyclotron that was, really refurbished from reconstructed from scratch, I would say.
Okay.
And the tandem, we made way less changes. But still, when you start to, like when you do renovation at your house, when you start, at some point you can't stop anymore because you find so many things that you need to change and upgrade and modify, and especially after it's many years that you have not done any renovation. So it was really, it is hell, pure hell.
Yeah.
So we discovered things that no human being can ever imagine that was done
Really?
over the years, like cables that were
Inside the
doing.
tandem.
No. Yeah, because they have to make some construction work, because since we will have higher beam intensities, we had to build thicker walls and things like this. So they were okay. They start digging, and so they just dismantled several old areas. And for instance, they found that instead of connecting to experimental holes with just cables, the cables were doing 1 kilometer away and 1 kilometer back. I don't know for which reason. Probably there was a reason when they did it, but nobody, I don't know, maybe what was done in the 80s. So nobody had the barest idea why these things were done.
Yeah.
So things, most of the time it's just stupid things like this. And terrible cables. So sometimes you would say you have noise in your detectors. You don't know, well, why is this so much noise? And then you find out why, because cables,
Yeah, I know. Also at the Luna, we have some cables that are very, very old, and we don't know why they are connected like this. But then everybody are afraid of taking them out because then things will not work.
never touch something that is working, you know. That's the main principle in experimental physics.
Yeah,
But when you are
exactly.
forced to, then the troubles start, let's say.
Yeah. I think people are joining.
So do we start sharp at
Maybe we can wait 2 minutes for the people
Okay.
to, and I will
Sure.
just give a brief introduction for you and you can start.
Okay.
Okay, Anna, I think we can start, right? And then if more people will
Yes.
join, they will. Okay.
Yep,
So
go ahead. How are you?
Yep.
Thanks.
So hello everybody. Today we will have a talk from Marco Cognata. He's a well-established researcher in experimental nuclear astrophysics. He's working in Laboratori Nazionali del Sud in Catania, Sicily, Italy. And he is the expert on the indirect techniques. So basically an alternative for the direct measurements, which are very difficult to achieve at astrophysical energies. And he will talk us about how to indirectly measure the same reactions with another and curious method that is called Trojan Horse Method. He in the recent years, he published many papers about different reactions. The most famous one probably is the carbon-12. And in this talk, he will focus on the newest result of the Trojan Horse Method. So, Marco, if you want, you
Thank
can
you.
start.
Thank you, Jacob. Thank you to everybody for giving me this opportunity to talk here. I hope you can hear me very well. Let's say. I got some cold, so maybe my voice will not be very, I had to start some time. Anyway, so as Jacob said, my field of expertise is nuclear astrophysics. And the nice things when you talk about nuclear astrophysics is that it's nuclear physics and astrophysics. So it's like binary. There is a strong connection between these two fields. And you can think like using nuclear reaction to understand astrophysics, and sometimes also you can use astrophysics to understand nuclear physics. And there are some famous examples on this. But in my case, I will talk mostly on nuclear reaction for astrophysics. So like the nuclear part of nuclear astrophysics. So this is an outline of my talk. So I will discuss a little bit because I guess you are quite expert in experimental nuclear physics, but it gives a little introduction about experimental nuclear astrophysics. Then I will talk a little bit about direct and indirect methods, because I guess most of you are familiar with direct reactions and direct measurements, and these are different. Sometimes you use direct reactions to make indirect measurements. So I want to make like clear this point, and especially discuss why sometimes it's useful not to make a direct measurement a nuclear reaction, but use an indirect method for this purpose. And I will talk mostly about two methods. There are a lot of indirect methods that were introduced over the years. Like I can mention at least 10 of them, but you know, there is not the whole day to talk about this, so I focus just on two, that is this Trojan Horse method. And also another one that is very closely related to Trojan Horse method, that is the ANC, the asymptotic normalization coefficient method. And for both, I will give you some experimental example. Just to show you what are the pros and cons of these two methods, and essentially like showing what are the opportunities and the kind of precision you can achieve by using these indirect techniques. So let's start with few notes about experimental nuclear astrophysics. So this chart here, you probably know very well. This is the chart of nuclei. And it's very interesting because there is like almost a one-to-one connection between the different areas of this nuclear chart and the processes, the astrophysical processes that lead to the synthesis of the nuclei of the isotopes that made up this table. Just to mention like the most relevant ones, like fusion reactions, that usually are those that produce nuclei up to the iron peak, so the iron region, and neutron-induced reactions that are instead responsible of the synthesis of nuclei that are heavier than iron. Among the fusion processes, there are like the most famous chains, the PP chain or CNO cycle and others that are taking place in more evolved systems, the carbon fusion, the triple-half reaction. And there are neutron-induced reactions like the R process and the R process that, for instance, are very, very relevant when you, especially the R process, when you consider explosive environments. So all these nuclear processes have a very connected with some astrophysical environment, with some star or some explosive environment, or even, for instance, the Big Bang nucleosynthesis sometimes. And this connection between nuclear physics and astrophysics is also apparent when you, for instance, make a plot of the abundances of the elements. The striking point in this kind of picture, where you show like the abundance as a function of the mass number of different nuclei, most of this can be explained taking into account the nuclear properties and astrophysics. This is very exciting how this that is coming from the observation of the solar system, so like on a scale that is even much larger than our Earth, is so strongly dependent on the microcosmos that is like the nuclear and subnuclear physics. So, and you see like the seesaw trend because of like even odd nuclei on these things and peaks corresponding to different burning stages in the stars. So it's very, very, very fascinating for me how the connection that you find between these branches of physics. That is totally unexpected, but it's so important. So nuclear astrophysics is essentially like a mixture of ingredients that are necessary to understand our universe. And between the ingredients, like nuclear physics is one of these, because of course you have nuclear models, you have astrophysical models, you have observations. Observation, we are in the era of multi-messenger astronomy, so observations can be like coming from, I don't know, measurement of neutrinos or gamma rays, even isotope in meteorite grains, so inside the meteorites that strike the Earth, our Earth. So really, there's a lot of different input, and in some sense, nuclear physics is a kind of glue that connects all these ingredients. And what is very important is that without nuclear physics, we really miss the connection between observations and astrophysical models. Because of course, to understand what is going on in a star, you have to make models because you cannot make stars in your lab. And but observations, for instance, like the abundance of the elements that you have seen before, depending on the cross-section of the reaction that are producing these elements. So if you want to have a constraint on the models to understand what is going on in the stars, you need to know cross-sections. It is a crucial ingredient, so that makes nuclear astrophysics so important. Usually, instead of using the cross-section, maybe you are more familiar with cross-section, but in nuclear astrophysics, people usually use the S-factor. And what's best than Wikipedia to find the definition of S-factor? Essentially, the connection between the cross-section and S-factor is given by this term here. That is essentially compensating for the strong Coulomb suppression of the cross-section when you have reaction between the charged particles. So usually the cross-section is going down exponentially when you have a reaction between charged particles. It's going down very quickly, reaching the values that are as small as neutrino cross-section sometimes. And so if you want to make nice plots, no way to plot the cross-section. If you use this factor, it's much better. Okay, it's not just this. The problem is that very often you cannot do the measurement at such low energies because, of course, as I said, cross-section are as small as the neutrino reactions induced by neutrinos. So usually it's necessary to use extrapolations. So, and it's hard to make an extrapolation when you have an exponential function because the uncertainty can be very large. Instead, if you have something that is smoother, like this factor, the extrapolation is much easier. So this is one of the reasons why over the years people introduced the definition of S factor. Okay, so after I've given a little bit of introduction about the general nuclear astrophysics, I will go a little bit more into the details. And let's start with the difference between direct and indirect methods. Okay. So usually when you want to measure cross-section, or as I said, an astrophysical factor that is connected with cross-section, you need a beam, a target, and a detector. So this is the basic ingredients if you want to measure a cross-section. Of course, life is much more complicated than this. But if you miss one of the ingredients, you cannot make a measurement most of the times, let's say. So it looks simple. In reality, it's complicated because your detectors are like covering only some part of your phase space, and you have like a small cross section, you have struggling the target, all these experimental issues. So in reality, it's extremely challenging, especially when you go to very low energies, because when you have charged particles, the cross-section are very low. So what is becoming especially bad is the signal-to-noise ratio, because the signal is going to zero, the background may be staying the same, unless you go underground, for instance, where you cut the background by several orders of magnitude. But if you have a above ground, even if you use the best shielding, it's very hard to have a reasonable signal-to-noise ratio. This is an interesting example from the past. Very old measurement. And this is interesting because it's showing I've called it like the paradox of compatibility, like in a Big Bang Theory episode, no? So it's interesting because just imagine you were like in the 60s, you did your measurement, like you get these small squares here, okay? They have big uncertainty, of course, but you have the solid theory. So you plot your data, you plot your theory, and is given by this dotted line here. You get the perfect agreement where the data are available. And you say, okay, I'm extrapolating, so this is the astrophysical factor. I'm extrapolating by several order of magnitude down to the astrophysical energies, for instance. This is given by this square here. And you are okay, because your theory is in perfect agreement with your data. So in principle, you think, okay, that's done. I'm happy. I can go to sleep. No. New measurement came out over the years, and they found a totally different trend. Nothing going down that quickly, but instead something going down like more flat in the astrophysical factor, of course. In the cross-section, you get something that is going down exponentially. And why? Because in reality, even sometimes, we think that theory is going to be very good, very robust, because it sounds so reasonable. Sometimes, theory, especially in nuclear physics, is not sufficient. It's not enough to understand what is going on. A new measurement pushing the limit, going as low as possible in energy, or I would say as close as possible to the astrophysical energy range, are crucial to understand what is going on. And this case was really a surprise. And they found out, for instance, this is connected. It's nice because this is like showing a connection between astrophysics and nuclear physics. The reason is coming from nuclear structure. This is deuteron-deuteron fusion going to gamma ray and helium-4. Everybody was thinking that, okay, you are populating an S-wave state helium-4. In reality, they found out that the wave function helium-4 has this state admixture that cannot be neglected when you go to very low energies. Everybody was saying, oh, this is so small, nobody cares. But this small, its concept of smallness is relative. It's not like something is small and you can neglect it. Because if you go to low energies, maybe it's not small anymore. So another effect that was found when you go to very low energies, apart, extrapolating into the unknown, it's electron screening. Well, this is kind of interesting because this is showing up when you go to very, very, very low energies. If you check this picture here, where you have helium-3 DP reaction, this is showing up, so when you go well below 100 keV. So this is like showing the astrophysical factor as you think it should look like. And that's the trend that you get when you do the real measurement. So what happens is that when you go to very low energies, you cannot neglect the electron degrees of freedom. This is something that everybody's doing when it's doing nuclear reactions, because electrons are far away from the nucleus, so they're slow. Nobody cares usually. But in reality, when the energies are very small, you cannot neglect these degrees of freedom anymore because the energies become, comparable in some sense. And what happens is that when your projectile is approaching and the distance and the classical distance of closest approach become of the same order of magnitude as the electron cloud radius, essentially your atom is neutral from outside, no? And so there is no repulsion. And no repulsion means that your cross-section is not going down exponentially or with the same steepness at least. When you go to the astrophysical factor, this means that the astrophysical factor is going up exponentially. And since the electron screening in the lab is very different from the one in the stars, because in the stars you have plasmas, in the lab you have molecules, atoms. So you cannot just say, okay, you have electron screening also in stars, so I can just take this astrophysical factor and do my simulations. You cannot do anything like this. So again, you need to extrapolate. And extrapolate is making problems, as I've shown you. So, to sum up, you have several problems, experimental issues, for instance, coming in the measurements, like the Coulomb suppression, sagging the target, electron screening. So people were thinking how we can get rid of these things. And the possibility is to use these indirect techniques. So the idea is that instead of measuring the reaction of interest, you measure a closely related process at a higher energies. And this way, you don't end up with the same issues. You have others, of course. You have no free meals, but at least the ones that I tried to explain so far are kind of absent. But of course, you need some nuclear reaction theory then to connect the cross sections that you measure for these indirect reactions and the one of astrophysical interest. Okay, and of course, whenever you have nuclear reaction theory, as I've shown you before, you can have some uncertainty, some model dependence. So these things have to consider it. There are a lot of indirect techniques, as I told you. Probably one of the oldest one is the Coulomb dissociation, but then there is the NC and THM that I told you about. There is the Oslo method, the surrogate reactions, time reversal. You can measure the time reversal of some reaction. So you can measure transfer reactions. There's a lot of this. So it's not enough time. So I'll go quickly. So if you go to the initial picture, where you have these three ingredients, the beam, the target, and the detectors to measure the cross-section, where you have indirect techniques, you go through a black box, and the only thing that is making light in this black box is nuclear reaction theory. So you have to add this additional ingredient that is necessary to connect these processes, let's say the direct and the indirect reactions. Okay, so a similar picture, but with something more. So it's a conservation of problems, let's say, a new principle of conservation. And when you go to radioactive ion beams, you still have issues. In principle, when you have these, when you need in radioactive ion beams, it's because the reactions are taking place in some explosive environment. So usually energies are much higher. So you shouldn't have so many troubles because of the suppression due to the Coulomb barrier. But the problem with radioactive ion beams is, of course, that the intensities are very low. So it is true that you don't have problem with the cross-section because probably is not so low, but the intensity is low. And since the yield is making by the product of the two, still the count rate or the signal-to-noise ratio is very low. And also there is especially big issues so far that it is impossible to measure reactions between a short-lived nuclear species and neutrons. And this is key, for instance, where you want to investigate processes like the R process, where you have these neutron captures on unstable nuclei, probably approaching the neutron blip lines. So again, sometimes you really cannot do the measurement. It's not just a matter that the measurement is complicated or the signal noise is low or you need to go underground or whatever. Sometimes you can really do the measurement. So you can only rely on indirect techniques. So just as a picture to show you just like a family picture of the most, of the closest indirect techniques, the Coulomb dissociation, the NC and Trojan Horse method. In the Coulomb dissociation, for instance, you use a virtual photon coming, for instance, from the lead nucleus to break a system, and you produce two particles coming out. Just imagine you have beryllium-7 on lead. Beryllium-7 get broken into pieces, helium-3 and helium-4. You measure these two products. If you go back in time, it's the same as you are emitting a gamma ray and you produce beryllium-7, not going backward in time. So this is interesting because if you go this way, from the exit channel to the entrance channel, you have this Coulomb suppression of these issues. If you go this way, you have a high, very large flux of virtual gammas, and you don't have any Coulomb suppression, so you can go to very low energies. Something similar is happening with the NC. Essentially is a technique where and I'll tell you more about this later on. In this case, you transfer a particle from one system to another, you populate some bound state. And this is a like kind of surrogate of a radiative capture reaction like the previous one. And similar to this the THM, and the main difference is that instead of populating some bound state, you populate an unbound state. Okay, so let's go a little bit more into the details, and let's start with the Trojan Horse method. Is my favorite in the indirect method. People can say, why did you use this fancy name? It's not because I'm a fan of the movie. That is, well, I don't know if you ever seen it. It's interesting, but maybe not the best movie. It's because the idea behind the method is that you use, and this is shown in this sketch here. So the idea is that you want to measure nuclear reaction like A plus X going to B plus B. But you don't want to measure like this directly. You want to hide this X inside another nucleus that you call Trojan Horse nucleus, of course, because it's like the Trojan Horse. Okay. When you hide this nucleus inside this other one, you can select some specific conditions where the process is quasi-free. What does it mean, quasi-free? For instance, just imagine you have a deuteron. A deuteron is a very dilute system, so the average distance with the proton neutron is very large. And there is no Coulomb interaction between the proton and neutron, okay? So if you select relative momentum between the X and S as a spectator, no, and the X is the participant. So if you select very small relative momentum between these two, this corresponds, by the uncertainty principle, to larger distances. And distances can be larger than nuclear interaction radius. So it means that these two particles, the neutron and the proton, or for instance, are not interacting. So that's why we say that they are quasi-free. It means that the reaction A plus X going to B plus B, it's taking place like S is not present. That's why it's called the spectator particle, okay? And you can use high energies, that is good. Instead of going like to kV scale, you can stay on the MeV scale, and still you are able to measure the reactional or astrophysical energies, because you'd have to spend some energy to break your Trojan Horse nucleus, okay? This is the basic principle. You end up, if you do the math, you end up in an equation like this, where this is the cross-section for the reaction with 3 particles in the exit channel. And this is the cross-section of the reaction that has astrophysical interest, okay? The only difference that this is because of the technique. This is missing the Coulomb penetration term, okay? Because when you just use your Trojan horse, you make it easy to get into the walls of Troy. And so it means that the cross-section is unaffected by the Coulomb barrier, in this case, let's say, by the wall, by the height of the walls. And so you have to put this back, this Coulomb barrier effect, okay, by inserting some penetration factor. And then you have an additional part, and this is where, the nuclear reaction theory is coming, okay? There is some proportionality factor you have to calculate. And this is like most of the time straightforward if you use the simple plane wave approximation. Usually this looks very easy. In reality, I can show you, but I'm not talking about this, the full equations that are way more complicated. This is more for theoreticians. But still, the important part is here, okay? So this is the amplitude, so the cross-section of the physical factor is calculated by taking the square of this, and you have the penetration to -1, okay? This means that if you put everything together, you measure something that is devoid of the Coulomb suppression of the cross-section, okay? There are some way that you can make this simple. For instance, where you have a narrow resonance reaction with narrow resonances, where the cross-section is dominated by the strength of the resonances. You don't need very much to know the trend or the exact trend of the cross-section. It's enough to have the area under the peaks that is essentially the strength, because these are used to calculate the reaction rate. And this introduces several, so this is the definition of resonance strengths. So essentially, this is the area under the peak of your Bragg beacon describing your resonance. And essentially, in this case, all the question that I showed you before becomes much simpler. Okay, it's just much, much simpler. And that's up, essentially in just a product. And here in the gamma, that is the partial width for the entrance channel, it's hidden the penetration factor. So again, you change the formulas, but I mean, the more important part of the idea is that you always compensate for the penetration of Coulomb barrier. And if you want to compare with the direct data, you have to put this back. Okay. Okay. The NC, it's very connected to this one. But instead of measuring reaction with the particles in the exit channel, you measure reaction with a gamma ray in the exit channel, so radiative capture reactions. If the process is peripheral, so if you are, for instance, low energy, and if your system is loosely bound, so this means that the proton is coming not very close to the nuclear well, okay? And so this means that it's not sensitive to the details of nuclear potential, because when you go far away for the nuclear well, essentially interaction is dominated by the Coulomb interaction that you can calculate. So this thing makes things much easier, of course, because the potential that you use to calculate the cross-section is much simpler. So this is just to show you some example. Essentially, if you want to calculate your cross-section, you have to always take the square of the amplitude, and the amplitude is given by some wave function describing the free particles, okay, or some distorted wave. So there's some operator that is telling you if it is, I don't know, dipole or quadrupole interaction. And then there is a term that is the overlap function that is essentially giving you the bound state wave function. If you write down this overlap function and you go to large distances with respect to the nuclear radius, this is essentially becomes a function called the Whittaker function. It's essentially an exponential, okay? And the term that is multiplying this is the asymptotic normalization coefficient. It's called asymptotic because this is the asymptotic form of the overlap function, okay? So essentially your cross-section becomes proportional to the overlap function, and you can extract the overlap function using transfer reactions. Because when you do a transfer reaction, this is an example where you transfer a particle P, like a proton, from some projectile, some target, for instance. If you write down the cross-section for this process, since you have two overlap functions, one for this bound state and the other one for this bound state, eventually your transfer cross-section is proportional to the square product of these two NCs, one for this system and the other one for this system. If you know one of them, you calculate this term. That is, you can use Fresco, for instance, or any this WBA code, for instance. Then you can deduce the NC of the process of interest, and you can calculate the cross-section. Okay. As I told you, there is a very strict connection between NC and Trojan Horse method, and this comes from the fact that in one case you have a transfer to a bound state, and this is the case of the NC, and a transfer to an unbound state. This is the case of Trojan Horse method. Okay, let's go to some experimental examples, just to show you how all these equations translate in when you do experiments. So I'll talk a little bit about a recent measurement we did, that is the aluminum-27 P-alpha and P-gamma reaction. So why this reaction is important? One of the reasons is when you have massive stars, you have several burning cycles. So the most famous is CNO cycle, but you can have others like the magnesium aluminum cycle, okay? So if you want to have a cycle, this must be closed, no? So you have to cycle along, these different reactions and these captures, okay? So this means that you have to have an high cross-section for the P-alpha reaction of aluminum-27. Otherwise, you don't close the cycle if you are having, for instance, radiative capture reactions. No, because in that case, you produce a silicon-28 and you're escaping from the cycle. Okay, so it's not a cycle. Because of the uncertainty on this cross-section, so you at present we don't really know if it is closed or not. Just to show you, these solid lines are giving you the range of the uncertainty is around 1 order of magnitude when you go to the astrophysical temperature of interest. So this is like showing the reaction rate, the ratio of the reaction rate. So like the upper lower limits and the best, like the recommended value, just to show you what is the uncertainty range And why you have this order of magnitude uncertainty? Because if you consider the cross-section at very low energy, this is dominated by several resonances, but for all of them, we don't have measurements, we have only upper limits. And upper limits means that it's like just a boundary condition, let's say. It's not a measurement, unfortunately. And this is because the Coulomb barrier is so large that you go to low energy, the cross-section is going, I don't know, 10 to minus 15 bar maybe, so very small. So in this case, we apply the Trojan Horse method in the simplified version that is used for reaction dominated by narrow resonances. So things gets easier, as I told you, because we only need to determine it's called the resonance strength. In this case, we use a deuteron, as I told you before, to transfer a proton, that is the participant, while the neutron is the spectator. And we have to fulfill this quasi-free condition, where the proton and neutron are essentially independent. Okay. So, just to show you some interesting physical pictures. So, when you measure this reaction, we measure it at 90 MeV. That is much higher than of course, the astrophysical energies that you need like to do the measurement at 20 kV, 30 kV, or 100 kV. So we go to 90 MeV, and this means that your signal to noise ratio is beautiful.
Sorry, Marco, you have 10 minutes.
Yes, thank you. So just to show you like this picture, so this is like simulations, the lines where your events should gather. You get two lines because we populated the magnesium 24 first excited state, but essentially everything is background free. Only if you go into the details. So this picture is showing you the Q value on one side and the energy mesh in one of the detectors on the other side. You see that there is a little tail that is background, okay? But it's orders of magnitude less than your signal. And this is the Q value picture, okay? It's showing you two nice peaks, the one of interest and some other stuff. And in the middle, you don't have nothing, but you have something that is coming from this background, okay? So even where you have indirect measurements, you have background, no? One of the things that we have to verify is that the process is quasi-free. If you remember, I showed you this graph, okay? That's the one we need if you want to apply our equations, okay? But of course, if you look at this is much different from these other graphs that you see here. This is instead you have fusion reaction, so you populate some states in silicon 29, and then these are decaying to magnesium 25 plus alpha, okay, or to magnesium 24 and helium 5. So this, since these are two-step processes, we call them sequential decays, okay? So how can we disentangle this process from the one of interest? One of the things you can do is make this relative energy plot, where you plot, for instance, the energy, neutron, and the relative energy between the neutron and helium 4, and the relative energy between neutron and magnesium 24. If you have states in magnesium 25 or states in helium 5, should get like horizontal lines or vertical lines. And you only see one spot. That is background, okay? So the other lines instead correspond to excited states in the system magnesium 24 plus alpha, okay? This is vertical lines. Other checks that can be done are more related to the proton-neutron momentum distribution. As I told you, if you consider small relative momenta, this means that proton and neutron are far away. So usually we check this momentum distribution and we consider only small momenta, because in this case, the process is quasi-free. Okay, so we have like comparison again with the theory, you find a very good agreement in some window, and that's the window that you consider for that analysis. A very important thing that is connected to the fact that this is nuclear reaction studies is that you can make angular distribution. Just imagine you are measuring at 100 kV and maybe you have 10 counts. In that case, you can do any angular distribution. But angular distribution are really important because they're telling you what are the spin parities of the states that you are populating. So you're doing nuclear spectroscopy. Okay, this is crucial because sometimes for these low energy states, you don't even know what is their spin parity. And this is like the excitation function that we got. So there are several peaks, okay? But the most interesting one is that we could observe a peak at the astrophysical energies, right at this peak. And this is coming from an 80 kV resonance. If you do some math, you end up with a table, okay, where the strengths from the literature in this column and the strength from our measurement. In this case, you see, instead of having upper limits for this, we could get a measurement for this 84 kV because we could observe a peak there. And for the other ones, we could set a smaller upper limit. All the other states I use as a cross-check to see if we have agreement, to validate our method. And you see that there is generally very, very good agreement between all of them. Okay, so this is a test that what we're doing is correct. And you calculate the reaction rate. Okay, and this is an example of the reaction rate. You see what we got. It's about 3 times lower than the one in the literature. Okay, so this means if you reduce the P alpha cross section, it means that it's less likely that this this magnesium aluminum is a cycle, because of course it's you are not closing the cycle, okay? Because the cross section that is closing the cycle is small, okay? Okay, let's skip all this and let's go to the NC. An example that I want to discuss about the NC is about the helium-3, helium-4 reaction, okay? Why this reaction is so important? It has been subject to many, many measurements over the years. In reality, this is an example where, sometimes astrophysics is doing a better job than nuclear physics. In fact, if you want to have like a solar model and want to predict the solar conditions, like for instance, the temperature in the center of the sun, you have, for instance, you can use the neutrinos for this purpose. But in order to connect the neutrino flux with temperature in the sun core, you need to know the cross-section of several reactions. And the largest source of uncertainty in the models is this one, it's the helium-3 alpha gamma, for which you need to get to errors very small, of the order of 3%, to match the accuracy that is coming from the measurement of the neutrino flux. But as you can see from the plot here, and this is showing like several measurements, and the gray line is telling you what is the usually accepted values. There is a large scatter, and this means that there are systematic uncertainties. And this means that that presently accepted interval, it's much larger than 3%. It's approaching like 7, 8% maybe. So this is needed to go to make a new measurement. And it can be very useful to help unraveling the issues, because as I told you before, you have the opportunity to measure the cross section really at 0 energy, because you are far away, no? Okay, so what we did was to measure this reaction, okay? So we had a lithium-6 target at Florida State University, where the previous measurement was done in my lab in Catania. And we detected neutrons coming out from this reaction. Now you can have two processes. You can, when you measure this reaction, you can either transfer a proton of helium-3 and populate beryllium-7 states, or you can transfer alphas from lithium-6 and you populate beryllium-7 states. So essentially what you get is that with the same experiment, you can measure 2 NCs for the helium-3, helium-4 reaction, and for the lithium-6 plus proton radiative capture reaction. So this is good when you propose an experiment, to some lab. You say, okay, you give me beam time, I do 2 measurements. So this is usually making a program advisory committee happy, Again, in this case, you have very clear signature, essentially no background. And if you plot the angular distribution, you see that this is kind of fit that you can get. We just focus on the forward and backward peaks. Okay, why? Because when you do the NC, this is the region that is most sensitive to the transfer reaction, while if you go to around 90 degrees, you can have compound nucleus reactions, okay? You can make several calculations, okay? Because you want to test your model dependence. And you end up with plots like this on the right. This is showing the change of the NC with the potentials that you use to fit your data, okay? And this is showing instead the spectroscopic factor. So the spectroscopic factor is changing by a factor of maybe 2, 3, while the ANC is essentially very stable when you change the potential. So our results are almost independent. So even if the fit is not good, you don't care very much. because there's so little sensitivity. And this is because you are not sampling the nucleus at short distances, but at large distances where the details of nuclear potential are negligible, okay? So from this measurement, we got this red point here. And so we're suggesting a value that is a little smaller than the literature, but still the uncertainty is a bit high. So we got 4% uncertainty that is still larger than your target. The one you remember, you need to get to like 3%. The good point is that this is totally independent of the other measurements. So you have totally independent systematic uncertainties. So it's helping, like, if you want to have an average, to squeeze a little bit the uncertainty. The main point is this kind of measurement to cut the uncertainty is to improve your theory, for instance. Like, so this is a list, so using better models to get better fit. This can reduce the width of the band that I've shown you before, and this is helping you to get better results. And the last slide that I want to show you, it's about this byproduct that is interesting, this Radion-6 proton reaction. So the red points and the blue points are two measurements. The red points is a measurement performed by a Chinese group that was suggesting the occurrence of some resonance at low energies in the S factor, okay? While the blue points are the lunar measurement taken underground, okay? So when you have data like this, you say, okay, then the error bars are large, but one is suggesting the presence of a resonance and the other one not. So who is right? So from our measurement, we got the green line, and essentially we got a very, very, very good agreement with the lunar measurement using an independent approach. This is showing you like the only way to improve the measurements and so to improve the input for astrophysical models is that the community is collaborating and with the aim of finding out the systematic uncertainties like the one that I've shown you in the DD fusion reaction at the beginning, and go to as low as possible in energy and get as better as possible measurements. Okay, so this is my summary. I hope I'm not spoken too much. So I've shown a little bit what is nuclear astrophysics. I've told you what is the difference between direct and indirect measurements, why indirect measurements are useful, and what are also the drawbacks of indirect measurements. And I've shown you two examples. That is this aluminum-27 P-half reaction and the helium-4 reaction. And the message that I want to leave is that you need really to have a deep understanding of nuclear physics. And so it means not just, measuring cross-section. It means to have experience with nuclear reaction theory and experience with like R matrix, spectroscopy, particle spectroscopy, gamma spectroscopy. So it's a very complex field. And you have to, like, as a big community, as a community, to work on these things, to trying to solve, to unravel the mysteries that the cosmos, our universe is like, or the questions that our cosmos is asking to us. Okay, thank you very much for your attention.
Thank you very much, Marco, for this very nice talk.